Okay, let's unpack this. Picture this. You're just starting out, really eager to write your very first lines of Python code. You've typed it all out, feeling pretty good about it. You hit run, and then your screen just explodes with this wall of bright red text.
Yeah, at that moment.
It's an error message, maybe a whole traceback. Your program stopped dead in its tracks. It feels like hitting a brick wall, right?
Absolutely.
Frustrating, confusing, maybe even a little defeating, you know?
Yeah.
What if that wall of text wasn't actually a dead end, but more like a message your program was sending you?
Exactly.
What if you could not just stare at it in confusion, but actually read it, understand it, and know exactly how to fix the problem?
That shift in perspective is it's absolutely critical when you're learning. Those red messages, yeah, they look intimidating at first, but they contain vital clues.
Right.
They are your program's way of diagnosing its own issues. Honestly, learning to interpret them is probably one of the most valuable skills a new programmer can develop.
And that's precisely the kind of empowering understanding we want to give you today. This deep dive is designed to be, well, like your personal tutorial in foundational Python concepts. We're cutting through the noise, taking the essential knowledge directly from some really key sources. The official Python 3.1, 3.4 documentation, specifically their sections on errors and exceptions.
Very important stuff.
A really practical guide to installing Python from Real Python, and the solid Introduction to Python Programming textbook by OpenStax.
Good sources. So our mission today is really to guide you through the absolute must-knows. We'll start right at the beginning with the maybe surprisingly complex first step of getting Python actually installed and ready to go on your computer.
Because you can't run code if you don't have the engine.
Exactly.
Then we'll dive headfirst into those errors, breaking down the different types you'll encounter, and crucially, how to handle them so your program can keep running, even when things get a little bumpy.
Yeah, resilience is key. After that, we'll build you up step by step with the fundamental building blocks. How programs interact with the outside world, using input and output. How you use variables to store and manage information, and understanding the different kinds of data Python works with. We'll then show you how to make your programs smarter by controlling the flow of execution. How to make decisions using if statements, and how to automate repetitive tasks with while and for loops.
And we'll wrap up our core foundational tour by showing you how to organize your code using functions and modules, and how to work with collections of data using two essential tools, lists and dictionaries.
Right. And our goal isn't just to, list these concepts, but to really demystify them. We want you to understand not just what they are, but how they function in practice, and most importantly, why they are so fundamental to building any program.
Yeah, the why is often missed.
By the end of this deep dive, you should feel much more confident approaching Python code, understand the essential vocabulary, and hopefully have a clearer map of where to start writing and debugging your own programs.
Okay, let's begin right at that first, sometimes underestimated hurdle, getting Python onto your machine.
You absolutely cannot run a single line of Python code without having the Python interpreter installed on your computer. Think of the interpreter as the translator.
Okay.
It reads your Python instructions and converts them into something the computer can actually understand and execute.
Yeah.
So, confirming you have it and installing it if you don't, that's step number one.
So the easiest way to check if you already have Python is to open up your command line or terminal, that text-based interface on your computer. Once it's open, just type Python version and press enter. On some systems, particularly Linux and Mac OS, you might need to try Python 3 version instead. Sometimes Python might point to an older version or just not be linked correctly.
Right. And if Python is installed and crucially accessible from your command line, you should see a message showing the version number, something like Python 3.0 by 112 or whatever version it is. If you get an error message like command not found or something similar, well, that means Python isn't installed in a way your command line can find it, and you'll need to install it.
And even if you do have Python, checking the version is still pretty important, right?
Oh, absolutely. Our sources are focusing on Python 3, which is the current standard. If your system somehow have a really old Python 2 version still hanging around, you'll definitely want to install a modern Python 3 alongside it.
Got it. So the actual installation process, it varies a bit depending on your operating system, yeah. Windows, Mac OS, Linux.
It does. Let's break down the common options for each one.
Okay, Windows first. What are the paths for Windows users?
For Windows users, you've got a few popular routes. The official installer from python.org is probably the most recommended, especially if you plan on doing more serious development down the line.
Okay.
You download an executable, file, .exe file from the official website. And when you run it, it gives you quite a few options during the setup.
And there's a key checkbox there, isn't there?
Yes, absolutely crucial. During that installation, look carefully for a checkbox that says something like Add Python to Path or Add Python 3.x to Path. Make sure you check this box.
Why is that so important?
Adding Python to your system's path environment variable basically tells Windows where to find the Python interpreter. It means you could just type Python or Python 3 in your command prompt from any folder, and it'll work. Forgetting this is a super common beginner mistake, and it leads to that command not found error later.
Ah, okay, so check the path box. Got it. What's the other Windows option? The Microsoft Store.
Right, the Microsoft Store. This is another option, and it's particularly good maybe for students, learners, or if you just want to quickly play around in the interactive shell. You just open the Microsoft Store app on Windows, search for Python 3.x, find the version you want, and click install. It's very quick.
But there are some limitations.
Yeah, the official documentation does note that the Microsoft Store package is, quote, intended mainly for interactive use. Because of how Windows Security Sandboxing works with Store apps, it might have some restrictions, like limited access to certain parts of the file system or the Windows registry.
So good for getting started fast, but maybe not for complex projects later.
Exactly. It's the quickest way to get Python running for simple scripts and interactive learning. But if you start doing more complex things like heavy file manipulation or system interactions, you might find you need the full control offered by the official installer from python.org.
Makes sense. And there's WSL, too.
Right, the Windows Subsystem for Linux, or WSL. If you're a Windows user but you actually prefer working in a Linux-like environment, you can install WSL, which basically runs a Linux distribution inside Windows. Then you just install Python within that Linux environment using the standard Linux methods we're about to talk about.
Okay, cool. What about macOS?
On macOS, again, the official installer from python.org is the go-to recommendation. Similar to Windows, you download a package file, it's a .pkg file this time, and run through the installer. This installer is good because it typically includes important dependencies that are useful for more comprehensive development work later on. You just go to the python.org downloads page, look for the latest Python 3 release, and grab the macOS 64-bit Universal 2 installer.
Okay. Is there a package manager option like on Linux?
Yes, very popular on macOS and also used on Linux, is using a package manager like Homebrew. If you already happen to have Homebrew installed, which many developers on Mac do, getting Python is super simple. Open your terminal and just type brew install Python.
And Homebrew handles everything.
Yep, Homebrew finds the right version, downloads it, sets it up, puts it in your path. It's a really clean and convenient way to manage software installations, not just Python.
Sounds good. Okay, now for Linux users.
For Linux users, Python is almost always pre-installed on your distribution. But like we said, the first step is still checking the version using Python version, or more likely, Python 3 version.
Right, because a pre-installed one might be older.
Exactly.
Yeah.
If you need a newer version or maybe a specific build that isn't the system default, the most standard way is using your distribution's native package manager. This is good because it keeps Python managed consistently alongside all your other system software.
So commands would differ slightly.
Yeah. For Debian or Ubuntu-based systems, the command is usually sudo apt update first to refresh the package lists, and then sudo apt install Python 3.x, replacing x with the minor version you want, like Python 3.11 or whatever.
Okay.
On Fedora or CentOS ASCII shell systems, you typically use sudo dnf install Python 3 or maybe sudo yum install Python 3 on older systems. The exact command really depends on your specific Linux distribution.
And there's a more hardcore option, too, building from source.
Yes, building from source. This is definitely more involved and usually reserved for advanced users or very specific server configurations. You download the Python source code itself, usually as a compressed file, like a .tar.xz file. Yeah. And then you have to unpack it, make sure you have all this necessary build tools and development libraries installed on your system. First, things like GCC, OpenSolevel, bzip2devel, libvidevel. You'd install those using your package manager.
Okay.
And then you run a sequence of commands in the terminal, usually something like .configure, then make, and finally sudo make install. It gives you the absolute latest version and fine-grained control. But it's generally overkill for most users starting out.
Gotcha. Stick to the package manager unless you have a really good reason not to.
Pretty much.
What about other ways to use Python, like on the go or just trying things out?
Yeah, worth mentioning a couple of things. For iOS users, there's a well-regarded app called Pythonista. It provides a surprisingly full Python development environment right on your iPhone or iPad.
Really?
Yeah.
Including libraries?
Yeah, it includes a lot of the standard library and even the documentation for offline use. It's actually excellent for learning and practicing Python when you're away from your main computer.
Cool. And for quick tests?
For just trying out small code snippets or experimenting without installing anything locally at all, there are tons of online Python interpreters or playgrounds. Just search the web for online Python interpreter. They're great for quick tests or sharing small examples, but obviously not suitable for building larger projects.
Makes sense. And one last thing on installation. Managing multiple versions.
Right. As you get more advanced, you might find yourself working on different projects that require different versions of Python itself or different versions of libraries. This can get complicated.
Yeah, sounds like it could break things.
It can. So there are tools designed specifically for this, like Pym. These are generally for more intermediate or advanced users, but they let you install multiple Python versions side by side on the same system and easily switch between them depending on the project you're working on. It keeps everything clean and separated.
Okay, that's good to know for the future. So, lots of ways to get Python installed.
Definitely. And as you can see, even this seemingly simple first step has multiple paths depending on your operating system and what you plan to do. Choosing the method that aligns best with how you want to use Python will just make getting started much smoother and ensure you have the right tools ready.
Because once Python is installed and you start typing that code, you are inevitably going to encounter those moments we talked about at the beginning.
The errors.
Yes.
They pop up.
They are a fundamental, unavoidable part of the programming process. And honestly, learning to read and understand those error messages is like developing a superpower. You need it.
Okay, so our sources make a clear distinction between two main categories of errors, right?
Yes.
Yeah.
Syntax errors and exceptions.
Let's start with syntax errors. What are they?
Syntax errors, sometimes they're called parsing errors, are the most basic type. They happen when you violate the fundamental grammatical rules of the Python language itself.
Like the structure is wrong. Exactly. The Python interpreter reads your code before it even tries to execute it. If the structure isn't right, if the syntax is incorrect, it just stops right there and tells you. It can't even begin to figure out what you want it to do because the instructions aren't written in a way it understands.
So things like forgetting a colon or misspelling a keyword like while instead of while, or leaving out a parenthesis or a quote.
Precisely those kinds of things. The documentation gives a classic example. While true print. Hello world.
Missing the colon.
Right. The structure for a while loop requires a colon after the condition, true in this case. When the Python parser sees the word print immediately after, true without that colon, it flags it as a syntax error.
And the error message it gives you is usually pretty helpful for these.
Generally, yes. The traceback for a syntax error will typically show you the file name, or it might say stin if you're typing directly into the interactive interpreter. It'll show the line number where the error was detected, the actual line of code itself, and often a little caret or pointer indicating the approximate location where it realized something went wrong.
Okay.
Now, in that while to print example, the pointer is usually under the P in print, but the actual fix is the missing colon before the print. So the pointer gets you close, but you still need to look at the surrounding syntax rules. The error message itself will also explicitly state that it's the syntax error.
Okay, so syntax errors are structural problems caught before the code even tries to run. What about the other category, exceptions?
Exceptions, on the other hand, are errors that are detected during the actual execution of your program. The code is syntactically correct. Python could read and understand the instructions just fine.
Okay.
But when it tried to actually do something based on those instructions, an issue arose. Something went wrong in the process.
And if an exception isn't handled, that's when you get the big traceback and the program usually crashes.
Yeah. Exactly. Unlike syntax errors, which prevent the program from even starting, unhandled exceptions crash a program that's already running. But the key difference is, as we'll discuss in a moment, you can actually handle exceptions to prevent those crashes.
Got it. Okay, the documentation gives some common examples of exceptions. What about trying to divide by 0?
That's a perfect example. The expression 10, 1, 0, is syntactically valid Python code. The structure is fine.
Right.
But when Python tries to evaluate the 1 TED part during execution, well, that operation is mathematically impossible. So Python raises a 0 division error. That's a specific type of exception.
And the traceback for an exception looks a bit different from a syntax error traceback.
Yeah, it's usually more detailed because it shows the path execution took to get to the error. It typically starts with traceback, most recent call last. Then it lists the sequence of function calls that led to the error, though for a very simple script, this might just be one level. It shows the file name, the line number where the exception occurred. the specific line of code that caused the problem, and then, crucially at the very bottom, the specific type of exception, like zero division error, followed by a descriptive message, like division by zero.
Okay, so if you see something like name error, name spam is not defined in that last line, what does that tell you?
That's another really common exception. It means your code tried to use a variable name spam in this example that hasn't actually been assigned a value yet. The structure of the code line might have been perfectly fine, but the operation of trying to use the value of a non-existent variable caused an error during execution. Python doesn't know what spam refers to.
Okay, and another one they mentioned is type error. Can only concatenate string, not int to string.
Right. That happens when you try to perform an operation, usually with an operator like +where on data types that aren't compatible for that operation. The example given is 2 + 2.
String plus integer.
Exactly. You're trying to use the plus operator. Python knows how to add two numbers, like 2 + 2, and it knows how to concatenate or join two strings, like hello plus world.
Yeah.
But it doesn't automatically know what you mean when you try to add a string and an integer too.
Yeah.
They're incompatible types for that operation, so it raises a type error.
This distinction between syntax errors and exceptions feels really, really important for debugging.
Oh, it is hugely important. When you get that red text, the very first thing you should do is look at the type of error at the very bottom of the traceback. Is it a syntax error?
Okay.
Okay, if it is, then you know the problem is with the structure of your code on or near the line indicated. Time to carefully check for things like missing colons, mismatched quotes or parentheses, correct spelling of keywords, proper indentation in the grammar of Python.
Right.
But if it's a different kind of error, like name error, type error, zero division error, value error, or something else, then you know your syntax is probably fine. The problem happened while the code was running. Now your focus shifts. You need to think about the values the variables held at that specific moment or the specific operation you were trying to perform.
Like, was I trying to use a variable before I gave it a value?
Yeah.
Did I try to combine incompatible data types? Did I try to divide by zero?
Exactly. Those kinds of questions.
Yeah.
Knowing the type of error directs your debugging effort significantly. It's like the program shouting, hey, your sentence structure is messed up. That's a syntax error.
Yeah.
Versus the program shouting, hey, the ingredient you told me to use, spam, isn't actually in the pantry. That's a name error. Or, hey, I can't mix oil and water using this whisk.
That's a type error.
That analogy really helps clarify it.
Yeah.
And you mentioned that exceptions aren't always fatal crashes. We can handle them.
Yes, absolutely. This brings us to the concept of exception handling, primarily using the try.except block. This is how you build resilience and robustness into your programs.
You basically anticipate that certain operations in your code might fail in a specific way. They might raise a particular type of exception. And you tell Python, okay, try to do this thing. If this specific problem happens, don't just crash. Instead, do this alternative thing.
So you put the code that might cause trouble inside a try block?
Exactly. The structure starts with try, followed by an indented block of code that you want to attempt to run. If all the code within that try block executes successfully, without raising any exceptions, then Python simply skips over any associated except blocks and continues execution with whatever code comes after the entire try.except structure, the happy path.
But if an exception does occur somewhere inside that try block?
Right. If an exception is raised at any point inside the try block, the rest of the code within that try block is immediately skipped. Execution jumps out of the try block.
Okay.
Python then looks down at the except clauses that follow the try block. It checks that the type of the exception that just occurred matches the type specified in any of the except clauses.
So you can specify which exception you're trying to catch.
Yes, you typically write except exception type, where exception type is this specific kind of error you're anticipating, like value error, zero division error, file not found error, etc.
Okay.
If Python finds an except clause that matches the type of the exception that was raised, it executes the code indented under that specific except block.
Right. The alternative action.
Exactly. After that except block finishes executing, the program doesn't crash. Instead, execution continues normally with the code that comes after the entire try.except statement. The error has been handled.
And what if no except block matches the type of exception that happened?
Good question. If an exception occurs in the try block, and Python looks through all the associated except clauses, but doesn't find one that matches the type of the exception, well, then the exception is not handled by this particular try, except block. It's considered an unhandled exception at this level. It then propagates outwards, meaning it might get caught by an enclosing try, except block if this one was nested inside another. But if it propagates all the way to the top level of the program without being handled by any except clause,
then it crashes.
And you get the standard traceback printed to the console.
So it really is like a conditional structure, but specifically for errors. Try this code. If a specific error happens, then do this instead.
That's a great way to think about it. And the source material provides a really common and illustrative example, often used for getting valid numerical input from a user. It uses a while true loop combined with try.except. Something like this. Python tot. Try user input true input. Please enter a whole number. It's input. Please enter a whole number. Hashtag this is the risky part. User input true input. Please enter a whole number. Print f you enter the number x. User input true input. Please enter a whole number. Print f you enter the number x. Except value error input. Please enter a whole number. Break. Hashtag exit loop if tree succeeded. Except value error. Except value error prints. Oops. User input true is not a valid whole number. Please try again.
Okay, let's walk through why this works so well. The while true loop.
That creates a loop that will just keep running indefinitely unless something inside it explicitly tells it to stop using break.
Got it. And inside the loop, we have the try.except. We ask the user for input using input, which, as we established, always gives back a string.
Correct. User input true will hold whatever the user typed as a string.
And the risky part, the line that might raise an exception, is x user input string.
Exactly. We're trying to convert the user's input string into an integer. Now, if the user types something like hello or 3.14 or 5, the infant function cannot perform that conversion. It doesn't know how to turn those strings into a whole number.
So int raises a value error.
Precisely. That's the specific type of exception int raises in this situation.
Okay, so let's trace the two paths. Path 1, the user types a valid whole number string like 42.
Okay. If user input store is 42, then int 42 succeeds. It returns the integer 42, which gets assigned to x. No value error is raised within the try block. Execution continues to the next line inside the try block, which prints the success message. Then it hits the break statement.
And break exits the loop.
Right. Break immediately terminates the innermost loop it's contained within, which is our while true loop.
Yeah.
The program then continues executing any code that comes after the while loop structure. Mission accomplished. Valid input received.
Okay, now path 2. The user types something invalid like apple.
Right. If user input star is apple, the line x equals int. Apple is executed. The int function fails and raises a value error.
Ah.
Because this exception happened within the try block, the rest of the code inside that try block, the print success message in the break statement, is immediately skipped.
Got it.
Python then looks for an except clause following the try block that can handle a value error, and it finds our except value error dot.
Yeah, and the code inside that except block runs instead.
Yes. The print oops message is executed, giving the user helpful feedback about what went wrong and prompting them to try again.
Okay.
After the except block finishes, execution continues after the entire try.except statement. In this structure, that's the end of the while true loop's body. Since the loop condition true is still true when we didn't break out, the loop simply repeats from the beginning, prompting the user for input again.
And it keeps looping like that, catching the value error and asking again until the user finally types something that int can successfully convert.
Exactly. It keeps asking politely until valid input is given.
That is a fantastic demonstration of how try, except makes a program more robust and user-friendly. It stops the program from just crashing because the user typed the wrong thing. It teaches the program how to recover gracefully.
Absolutely. It's a fundamental pattern for validating input or handling situations where external factors might cause errors, like trying to open a file that doesn't exist.
And you mentioned you can have multiple except clauses.
Yes, you can stack them up. If the code in your try block could potentially raise several different types of exceptions, you can provide a separate except block for each one you want to handle specifically. Python.
Hashtag code that might raise value error or type error. Result, risky operation data.
Print handling a value error specifically.
It's handling a type error specifically. Except exception as E. Hashtag catch other types, maybe log them. Print an unexpected error occurred.
Python will execute the first except block whose type matches the exception that occurred. Only one except block is ever executed for a single exception event.
The sources also mention getting access to the exception object itself, using as...
Right. Sometimes you want more information about the error than just its type. You can capture the exception instance using exception type as variable name. Inside that except block, the variable name will refer to the actual exception object, which often contains useful attributes, like an error message. Python.
Hashtag .code that might fail. .x accepts zero division error as error. Print f caught an error. Error.
Hashtag error will hold the message division by 0.
This is common for logging errors or providing more detailed feedback.
And there was advice about being specific versus using a broad exception. Why is being specific generally better?
Well, exception acts like a catch-all. It will catch almost every type of standard exception. Well, this might seem convenient, like I'll just prevent any crash. It can actually be dangerous because it can hide problems you weren't expecting.
Imagine your code has a subtle bug that, under certain rare conditions, causes it to run out of memory, raising a memory error. Or maybe a logic error leads to an index error when accessing a list. If you've just used a broad exception, your program might catch that memory error or index error, print a generic "an error occurred" message, and then try to limp along.
So you wouldn't necessarily know that a serious, unexpected problem happened.
Exactly. You might not realize the true underlying issue. By catching specific exceptions that you anticipate and know how to handle gracefully, like value error from user input or file not found error when opening a file, you're dealing with the known risks.
Right.
If an unexpected exception occurs when you didn't specifically plan for, you often want it to be unhandled by your specific except clauses. You want it to propagate up and potentially crash the program, giving you a full traceback. That crash is your alert system. It's telling you, hey, something completely unexpected happened here that I wasn't prepared for. There's a deeper problem you need to investigate and fix.
Okay, that makes perfect sense. Be specific to handle known, recoverable issues, but let unknown, potentially serious issues make noise so you notice them.
Precisely. It leads to much more robust and maintainable code in the long run. You handle what you can, and you learn about the things you couldn't anticipate.
The source material also discusses the finally clause. What's its role?
Yes, finally. The key takeaway for finally is that it defines a block of code that is guaranteed to execute no matter what happens within the preceding try and except blocks.
Guaranteed. Like always.
Always. It runs if the try block completes successfully without any exceptions. It runs if an exception occurs and is caught by an except block. It even runs if an exception occurs in the try block and is not caught by any except block. The finally block executes just before that unhandled exception propagates up and potentially terminates the program. It also runs if the try or except block executes a break, continue, or return statement. The finally runs before control is actually transferred.
Wow. Okay, so what's the main use case for something that absolutely must run?
The most common and crucial use case is for cleanup actions. Resource management. Imagine you open a file to read or write data, or you establish a connection to a database or a network service. These are resources that need to be properly closed or released when you're done with them, or even if an error occurs while you're working with them.
Like closing the file handle.
Exactly. Putting the code to close the file or release the network connection inside a finally block ensures that cleanup action happens, regardless of whether the operations in the try block succeeded or failed. Python.file, none. Hashtag initialize file variable.
File open important data.txt.w. Hashtag write some data. Maybe an error occurs here. File.write, this is critical info.in. Hashtag maybe another error happens. The result at 100 is 0, except IO error as E. Print if error writing to file.e.
The finally block.
Yeah.
If file is not none not file.closed, none and not file.closed, file.closed.del, print file is not open or already closed.
In this example, whether the write succeeds or an IO error occurs during writing, or even if that unexpected zero division error happens, the finally block will still execute. It checks if the file variable was successfully assigned an open file object, and, if so, ensures file.close is called. It guarantees the cleanup.
That makes total sense. It's like making absolutely sure you lock the door when you leave the house, even if you tripped on the way out or forgot your keys inside the try block.
Exactly. It's essential for preventing resource leaks and ensuring your program leaves things in a clean state.
The sources also briefly mention the raise statement. We've seen exceptions being raised by Python itself, but raise lets us do it.
Yes. The raise statement allows you to manually or programmatically trigger an exception yourself. You use it like raise exception type, optional descriptive message.
Why would you want to intentionally cause an error?
It's used to signal that a specific error condition has been met within your own code, according to the logic you've defined. For instance, if you write a function that's supposed to process positive numbers only, you might check the input at the beginning. If the input number is negative, your function can't proceed correctly, so you raise value error. Input number must be positive.
Okay. So it's a way for your function to clearly report, hey, you gave me bad data, or Something went wrong according to my rules.
Precisely. It allows functions and methods to communicate error conditions back to the code that called them, using the standard exception mechanism. The calling code can then potentially use a try.except block to catch the specific exception you raised.
So try.except is mostly about handling exceptions that Python or other libraries might raise, while raise is for triggering exceptions in your own code for others or other parts of your code to potentially catch.
That's a great summary. Try, except, finally, and raise are really the cornerstones of robust error handling and control flow in Python. Getting comfortable with them is absolutely key to writing programs that don't just fall over when faced with unexpected inputs or situations.
Okay, so we've got Python installed, theoretically, and we now have a strategy for dealing with errors when they inevitably pop up. Now, for the fun part, actually writing some basic code that does something.
Right. At its absolute core, a computer program is just a sequence of instructions or statements that Python executes one after the other, typically from the top of the file down to the bottom. And many of these statements involve expressions. These are just pieces of code that evaluate to a specific value. Think 5 plus 3, or hello plus k plus world, or maybe useridge365. These expressions produce results.
And the most fundamental way for a program to communicate back to us, to show results or messages, is through output. In Python, that's primarily done using the print function.
Yes, the print function. And it is a function which, crucially in Python 3, means it absolutely requires parentheses after the name. As the source material points out, trying to do print hello, like you might have in older Python 2 code, will give you a syntax error.
Right. Got to have the parentheses. .print hello.
Correct. And you can print multiple things at once just by separating them with commas inside the parentheses. Print, my name is Python.
And by default, print sticks a single space between each of those items when it displays them.
It does, but you have control over that. Print has optional arguments. One is sep, which stands for separator. You can set sep to a different string to use instead of a space. For example, print user example com sep at would output user at example at com.
Oh, neat. Okay.
Another really useful optional argument is end. This controls what print puts at the very end of the line after printing all the items. By default, end is set to the new line character, n.
Which is why each print call normally starts its output on a fresh line.
Exactly.
Yeah.
But you can change it. If you set end, an empty string, print won't add a new line, so the next print statement will continue on the same line. Or you can set end to any other string you want.
So print loading, end, followed maybe later by print, done, would appear on a single line as loading, done.
Yep. And something like print date 2023 10/26 sep ndn would output date.20231026 nd followed by a new line. Gives you a lot of flexibility for formatting your output nicely.
That end argument seems particularly useful.
Yeah.
Okay, so that's output the program talking to us. How do we talk to the program? Input.
Input, yes.
Yeah.
This is primarily done with the input function.
The usage is input. Optional prompt message, right? The string you put inside the parentheses gets displayed to the user as a message or a question, and then the program just pauses, waiting for the user to type something in the console and hit the enter key.
Correct. And the absolute most crucial thing to remember about input, something that trips up nearly every beginner, is that whatever the user types, no matter what it looks like, input, always returns it to your program as a string. SCR.
Always a string, even if they type numbers.
Always. If the user types 123 and hits enter, the input function gives your program the string 123, not the numerical integer value 123.
So if you want to use that input to do math, you must explicitly convert it first using int or float.
Exactly. Which brings us right back to why understanding type conversion and how to handle potential value error exceptions with try, except is so important when dealing with user input. You almost always need to convert input if you expect a number.
Got it. Always returns a string. So once we have this input string, or maybe the result of some calculation, we need a way to store that information, right? To use it later.
Yes. And that's the fundamental role of variables.
Okay. Variables are...
You can think of variables as basically names that you give to specific locations in your computer's memory where you can store values. The way you create a variable and store a value in it is using the assignment operator, which is the single equals sign.
Single equals for assignment. So username equals Alice.
Perfect. That creates a variable named username and stores the string value Alice in the memory location associated with that name.
And once you've assigned a value to a variable, you can just use the variable's name later in your code to refer to that stored value.
Exactly. So if you previously did city, Chicago, later on you can write print, the user city is city, and Python will look up the value currently stored in the city variable and print that.
Makes sense. Are there rules for what you can name your variables?
Yes, there are specific rules. Variable names in Python can contain letters, both lowercase AZI and uppercase AZ, digits 0, 9, and the underscore character.
Okay.
However, a variable name cannot start with a digit. My var is fine, var1 is fine, but one var is not allowed. That would be a syntax error.
And they can't be Python special keywords, right? Like if, else, while, for, def, class, import, return. That whole list.
Correct. Keywords have specific meanings in the Python language, so you can't use them as names for your variables. Trying to do something like if 5 will result in a syntax error.
Also, Python is case sensitive.
Very important point, yes. Python treats uppercase and lowercase letters as distinct. So a variable named myVariable is completely different from a variable named myVariable or myVariable. You have to be consistent with capitalization.
Okay. And what about style? Is there a recommended way to write variable names? The source mentioned PP8.
Right, PP8 is the official style guide for Python code. It provides recommendations to make code more readable and consistent across different projects and developers. For variable names, and function names too, PP8 strongly recommends using snake case.
Snake case.
Yeah, it just means all lowercase letters with words separated by underscores. Like first name, item count, users are active, total, price after discount. Following this convention makes your code much easier for you and others to read and understand compared to mixing cases or using hyphens, which aren't allowed in names anyway.
Okay, snake case for variables. Seems like a lot of little rules, but variables are obviously fundamental.
They absolutely are. They are the backbone of how you manage and manipulate data in pretty much any program. You take input, store it in variables, you perform calculations using values from variables, and store the results in other variables. Then you use print to output the values currently held in those variables. You really can't build anything interesting without using variables effectively.
Building on that, let's talk a bit more about the different kinds of data, the different types that we can store in those variables. Python handles various types quite automatically, right?
It does. Python is dynamically typed, meaning you don't usually have to declare the type of a variable explicitly. Python figures it out based on the value you assign. The core built-in types are the ones you'll use constantly.
Okay, like integers.
Right, integers, int, for whole numbers. These can be positive, negative, or 0, like 1, -5, 0, 1, 2, 3, 4, 5.
And numbers with decimal points.
Those are floating point numbers, or floats, like 3.14, -2.5, 0.0, or even numbers written in scientific notation, like 1.23 E4, which means 1.23 times 10 to the power of n-4.
Got it. And text.
Text data is represented as strings, STR. A string is just the sequence of characters. You create string literals by enclosing the characters in matching quotes. You can use single quotes, hello, double quotes, world, or triple quotes.
Triple quotes.
Yeah, either triple single quotes or triple double quotes. These are special because they allow the string to span multiple lines easily. They're very commonly used for writing docstrings, which are documentation notes for functions and modules, but they work for any multi-line string literal.
Okay. And strings can contain special escape sequences too, like N for a new line character or T for a tab character.
Exactly. Those let you represent characters that are hard to type directly.
And the last core type, Booleans.
Right. Booleans. There are only 2 Boolean values, true and false. Note the capitalization, they must start with a capital letter. Booleans are absolutely fundamental for decision-making and controlling the flow of your program, as we'll see later with if statements and while loops.
We touched on type conversion briefly when we talked about input, always giving a string. Python provides functions to explicitly convert values between these types.
It does. The main ones are int, float, stusr, and bool. You pass the value you want to convert inside the parentheses.
So int 123 gives you the integer 123, and float 3.14 gives the float 3.14.
Correct. But remember the potential pitfall. If the string doesn't represent a valid number of the target type, you'll get a value error. For example, int hello raises a value error. And interestingly, int 3.1 also raises a value error because 3.1 isn't a valid representation of a whole number integer. You'd have to convert it to a float first. float 3.14, and then potentially to an int if you wanted to truncate it.
Ah, okay. What about converting between the number types?
Int 4.5 will truncate the decimal part and give you the integer 4. Float 5 will convert the integer 5 into the float 5.0.
And converting numbers to strings.
Easy enough with string.
Yeah.
2.123 gives you the string 123. String 1.14 gives you the string 3.14. This is often needed when you want to combine numbers with text for printing.
What about converting things to Booleans using bool?
The bool function is interesting. It follows specific truthiness rules in Python. Most values, when passed to bool, are considered truthy and will result in true.
Most things are true. What's false?
Only a specific set of empty or zero values are considered falsy and result in false when converted using bool. These include the integer 0 and the float 0.0, the empty string, an empty list byte, an empty dictionary, the special value none, which represents the absence of a value, and a few other empty collection types. Pretty much everything else, non-zero numbers, non-empty strings, non-empty list dictionaries, etc., evaluates to true when converted to a Boolean.
That's a really handy rule of thumb to know, especially for if statements later. Okay, now, what happens when we start mixing these different data types in operations like addition or multiplication?
Good question. When you mix integers and floats in arithmetic operations like addition, plus, subtraction, multiplication, division, modulo, percent, exponentiation, Python generally promotes the integer to a float before performing the operation. The result will typically be a float.
So 5 plus 2.0 results in 7.0.
Exactly. The integer 5 is effectively treated as 5.0 for the addition.
But strings and numbers usually cause problems if you mix them directly, like 5 plus 2, giving that type error we mentioned.
Precisely. For most operations, you can't directly combine strings and numbers. You need to explicitly convert one of them to match the type required by the operation you intend.
So if you want to join the string 5 and the number 2 to get the string 52,
you need to convert the number to a string first, 5 plus string 2. That results in the string 52.
And if you want to perform numerical addition using the value represented by the string 5 and the number 2,
you need to convert the string to a number first. Init 5 plus 2, that results in the integer 7.
Makes sense. You have to be explicit about your intent, except there's that weird exception with strings and multiplication.
Yes, string repetition. That's a special case. If you multiply a string by an integer, or an integer by a string, Python interprets it as repetition. Ha3 results in the string. Ha ha ha. It's just a convenient shorthand provided by the language.
Okay, good to know. Let's focus a bit more on the purely numeric operations. We have the standard addition, subtraction, multiplication, but Python has different kinds of division.
It does. There are two main division operators. First, there's true division, which uses the single slash whereas. True division always results in a float, even if the division results in a whole number.
Always a float. So 10.2 is 5.0, not 5.
Correct. And 7.4 is 1.75.
Okay. What's the other division operator?
It's floor division, which uses the double slash or. Floor division performs the division and then rounds the result down to the nearest whole number, integer. It effectively gives you the integer quotient.
Rounds down. So 7.4 would be 1, since 74 is 1.75.
Exactly. And 10.2 would be the integer 5. 1.4 would be 0. It always truncates towards negative infinity, so even with negative numbers, it rounds down. Negative 7.4 results in negative 2, because negative 1.75 rounded down is negative 2.
Okay, floor division gives the integer part rounding down, and there's also the modulo operator.
Yes. The modulo operator %, often pronounced mod, it gives you the remainder of a division operation.
The remainder. So 7 plus 4 would be?
It would be 3, because 7 divided by 4 is 1 with a remainder of 3.
Okay, and 10%.
That would be 0, because 10 divides evenly by 2 with no remainder. The modulo operator is incredibly useful for tasks like checking if a number is even or odd, if number pursued is 0, it's even, or for cyclic operations.
Got it. And exponentiation, raising to a power.
That's done using the double asterisk. So 2, 3 means 2 raised to the power of 3, which evaluates to 8. 5, 2 is 25.
And for dealing with floats specifically, there's a round function.
Yes, the built-in round function is very handy. If you call round number with just one argument, it rounds the float to the nearest integer. If you provide a second argument in digits, like round number in digits, it rounds the number to that specified number of decimal places. Round 3.141592 gives 3.14.
Now, speaking of floats, the sources mentioned a potential issue.
Yeah.
Something about them not always being perfectly accurate.
Yes, this is a really important concept to understand about floating point arithmetic in virtually all programming languages, not just Python. It stems from the way computers represent decimal numbers using binary base 2 internally. The issue is that some simple decimal fractions, like 0.1, 1/10, cannot be represented exactly as a finite sum of powers of 2. Just like 13 cannot be represented exactly as a finite decimal, it's 0.333, 110 cannot be represented exactly as a finite binary fraction.
So when I type 0.1 in my code, the value stored as a float isn't precisely 0.1.
No, it's usually stored as a binary approximation that is incredibly close to 0.1, but not mathematically identical. This can lead to tiny, almost imperceptible round-off errors accumulating in calculations.
The documentation showed an example like 0.1 plus 0.2 maybe not being exactly 0.3.
Right. Due to these tiny representation inaccuracies, the result of 0.1 plus 0.2 might be something extremely close to 0.3, like 0.30000000004.
And where does this usually bite you? When you try to compare floats for exact equality.
Exactly. That's the main place beginners run into trouble with this. If you perform some calculations and then try to check if the result is exactly equal to another float using like this 0.1 plus 0.2, p.3, that comparison might unexpectedly evaluate to false because of that minuscule internal difference.
So what's the workaround? How should you compare floats?
For most practical purposes, instead of checking for exact equality, you should check if two floats are very close to each other, within a small tolerance or margin of error, often called epsilon.
How do you do that?
A common way is to check if the absolute value of the difference between the two numbers is less than some very small number. For example, abs AB 1E9, where 1E9 is 0.0000000001. If the difference is smaller than that tiny tolerance, you can consider them equal enough for your purposes.
Okay, that's a crucial takeaway for working with floats. Understanding these data types, how Python handles operations between them, how to convert them, and being aware of potential quirks like floating point inaccuracies seems absolutely fundamental to writing correct and reliable code.
It really is. Once you have a grasp on how to store and manipulate these individual pieces of data using variables and understanding their types, the next big step is making your program dynamic and intelligent. Programs rarely just execute instructions straight down. They need to make choices and repeat actions based on conditions.
And this is where those Boolean values, true and false, really come into their own right, along with comparison operators.
Absolutely. Comparison operators are the tools you use to ask questions about the relationships between values. They evaluate these relationships, and the result is always a Boolean, either true or false.
So we have, for checking equality is A equal to B.
Right. And for inequality is A not equal to B.
Then the standard mathematical comparisons. Fall. For less than, greater than, less than or equal to, and greater than or equal to.
Correct. And the result of any expression using these operators is always either true or false. 10 equals 10 evaluates to true, 510 evaluates to false, age equal 21 evaluates to true or false depending on the value of age.
Yeah, there's a critical warning in the source material about mixing up the comparison operator, double equals, with the assignment operator, single equals. That's a common mistake.
Oh, incredibly common, especially for beginners. Remember, single equals is for assigning a value to a variable. Double equals is for comparing two values to see if they're equal.
So if you accidentally write if x equals 10 instead of ic equals 10,
that's actually a syntax error in Python in most contexts where a condition is expected, because an assignment statement doesn't produce a true-false value in the way if needs. The interpreter helps you catch that one. A more subtle mistake mentioned is something like isn num equals 10. Someone might think this checks if num is 10 and stores the result in is.
but that's not what it does.
No, that's chained assignment. It assigns the value 10 first to num, and then assigns the result of that assignment, which is 10, to isn. So both variables end up being 10. If you wanted to check if num equals 10 and store the true-false result, you'd need to write isn num equals 10, using the comparison operator and parentheses for clarity.
Okay. Good distinction. Now, often you need to combine multiple conditions. That's where logical operators come in. And or not.
Exactly. These operators work with Boolean values, true or false, and produce a Boolean result.
And requires both sides to be true.
Correct. Condition 1 and condition 2 evaluates to true only if both condition 1 is true and condition 2 is true. If either one or both of them is false, the entire and expression becomes false.
Okay. And or is more lenient.
Yes. Condition 1 or condition 2 evaluates to true if at least one of the conditions is true. It only becomes false if both condition 1 and condition 2 are false.
And not just flips the value.
Right. Not condition simply invrimps the Boolean value. Not true becomes false, and not false becomes true.
These comparisons and logical operators form the basis for decision-making structures in Python. allowing your program to take different paths depending on whether certain conditions are met.
Precisely. The most fundamental decision-making structure is the if statement. The basic syntax is if condition. #body.
So the code indented under the if line, the body only gets executed if the condition right after the if evaluates to true.
Exactly. If the condition evaluates to false, the entire indented body block is skipped, and Python just continues execution with the next line of code after the if block.
What if you have a simple choice between two alternatives, like do this if the condition is true, otherwise do that?
For that, you use the if-else statement. The structure is if condition, #body1 else, #body2.
Okay.
If the condition evaluates to true, the code in body 1 under the if is executed and body 2 under the else is skipped. If the condition evaluates to false, then body 1 is skipped and the code in body 2 is executed instead. With an if-else structure, one of the two blocks, either the if block or the else block, will always execute.
Got it. But what if you have more than two possibilities, like checking multiple conditions in sequence?
That's where chain conditionals using if-else come in. Elif is short for else if. The structure look like this. Python.
#body1 runs if condition 1 is true.
#body2 runs if condition 1 is false and condition 2 is true.
#body3 runs if 1 and 2 are false and condition 3 is true. You can have more Ellison.
#bodyN runs if all preceding conditions were false.
So Python checks the conditions one by one from top to bottom.
Exactly. It checks condition 1. If it's true, it executes body 1 and then skips the entire rest of the elif and else chain. Execution jumps to whatever comes after the whole structure.
Okay.
If condition 1 is false, it then moves on to check condition 2. If condition 2 is true, it executes body 2 and skips the rest of the chain. If condition 2 is also false, it moves to condition 3 and so on.
And the final else block?
The final else block is optional. If it's present, its body N, is executed only if all the preceding if and elif conditions evaluated to false. Crucially, in an if-elif-else chain, only one block of code, at most, will ever be executed, the one corresponding to the first condition that evaluates to true, or the else block if none were true.
This seems perfect for scenarios like grading based on score ranges or classifying different types of input. If it's A, do this, else if it's B, do that, else if it's C, do something else. Otherwise, handle the default case.
Exactly. It's a very common and powerful pattern. And you can also nest these structures.
Nesting.
Yeah.
Meaning putting an if statement inside the body of another if or else.
Yes. You can put an entire if-else or if-elif-else structure within the indented block of another if statement or an elif or else block. This allows you to build more complex layered decision logic. If condition A is true, then check condition B. If B is true, do X, else do Y. Otherwise, if A was false, check condition C, and so on.
Okay, that allows for pretty intricate logic. The source also mentions something called a conditional expression, like a one-line if-else.
Ah, yes, the ternary operator or conditional expression. It's a concise way to write a simple if-else statement when the main purpose is just to assign one of two values to a variable based on a condition. The syntax is value if true, if condition else, value if false.
How does that work?
Python evaluates the condition. If it's true, the entire expression evaluates to value if true. If the condition is false, the entire expression evaluates to value if false. It's most often used in assignments like status adult if age 18 else minor. This is just a shorter way of writing.
Python.
If age 18, status adult. It's handy for simple cases, but can become unreadable if the expressions or condition get too complex.
Got it. Now, with all these operators, arithmetic, comparison, logical, and potentially complex expressions, we need to think about the order they get evaluated in, right? Operator precedence.
Absolutely. Just like in mathematics, where multiplication happens before addition, Python has rules about the order in which operators are evaluated. Generally, arithmetic operators have higher precedence than comparison operators, which in turn have higher precedence than logical operators. Among logical operators, not is evaluated first, then and then or.
That sounds like it could get confusing quickly.
It can, which is why the best practice, strongly recommended by the sources and developers everywhere, is to use parentheses liberally to explicitly group parts of your expression. Don't rely on remembering the exact precedence rules. Use parentheses to make the order of operations clear and unambiguous, both for Python and for anyone, including your future self, reading the code. A plus BC is much clearer than relying on knowing multiplication comes before addition if you wrote A plus BC but meant the addition first. Clarity trumps relying on implicit rules here.
Good advice. Use parentheses. Okay, so that covers making decisions. What about repeating actions? Loops.
Loops are fundamental for automation. Python provides two main types of loops. the while loop and the for loop.
Let's start with while. How does that work?
The while loop has the structure while condition. #body. It works like this. Python first evaluates the condition. If the condition is true, the indented code block, the body, is executed. After the entire body finishes executing, Python goes back up and evaluates the condition again. If it's still true, the body executes again. This cycle repeats. Check condition, if true, execute body. Check condition, if true, execute body.
Until when?
Until the condition evaluates to false. As soon as the condition is checked and found to be false, the loop terminates immediately. Python skips the body and continues execution with the first line of code after the entire while loop block.
So this means something inside the loop's body usually needs to change whatever the condition is based on.
Yeah.
Right? Otherwise, the condition might just stay true forever.
Absolutely. Critical point. If the condition starts as true and nothing inside the loop's body ever causes it to eventually become false, then the loop will just keep checking true, running the body, checking true, running the body forever. That's an infinite loop.
The program gets stuck.
Yep. It gets stuck executing that loop endlessly, and you'll usually have to manually interrupt or kill the program. So when writing a while loop, you must ensure there's a mechanism within the loop's body to eventually make the condition false. Often this involves incrementing or decrementing a counter variable or changing a flag variable based on some event.
Okay, that's the while loop repeats as long as the condition is true. What about the for loop?
The for loop is designed specifically for iterating over the items in a sequence. A sequence could be the characters in a string, the items in a list, or a sequence of numbers generated by range, among other things. The structure is for loop variable in sequence, #body.
How does that work?
The for loop takes the sequence you provide. For each item in that sequence, one by one, it does the following. 1. Assigns the current item to the loop variable. 2. Executes the indented body of the loop. It automatically handles moving to the next item in the sequence for the next iteration. When there are no more items left in the sequence, the loop terminates.
So if I have a list, my list ADC, and I write for letter in my list print letter, what happens?
The loop will run 3 times. First iteration, letter will be assigned A, and print letter will output A. Second iteration, letter will be assigned B, and print letter will output B. Third iteration, letter will be assigned C, and print letter will output C. Third iteration, after that, there are no more items in my list, so the loop finishes.
That seems much simpler for iterating over existing collections than trying to manage indices with a while loop.
It generally is. For loops are considered more Pythonic and readable when your goal is simply to process each item in a known sequence.
You mentioned the range function is often used with for loops.
Yes, very often. Range is a convenient way to generate a sequence of numbers, which is useful if you want to repeat an action a specific number of times or if you need to work with numerical indices.
How does range work again?
It can be used in a few ways. Range, stop, generates numbers starting from 0 up to but not including the start value. So range 5 generates the sequence 0, 1, 2, 3, 4, range, start, stop. Generates numbers starting from start up to but not including stop. Range 2, 5 generates 2, 3, 4, range, start, stop, step. Generates numbers starting from start, incrementing by step each time until it reaches or passes stop. Range 1, 10, 2 generates 1, 3, 5, 7, 9. You can also use a negative step to count down. Range 501 generates 5, 4, 3, 2, 1.
So for I, in range 3, print hello would print hello 3 times.
Exactly, because range 3 generates the sequence 0, 1, 2, and the loop body runs once for each of those numbers, though the loop variable I isn't actually used in the print statement in this case.
Just like if statements, can loops be nested? A loop inside another loop?
Yes, absolutely. You can put a while loop or a for loop entirely inside the body of another loop. This is very common for processing two-dimensional data structures like a grid or a list of lists.
How does the execution work then?
The outer loop starts its first iteration. Then, the entire inner loop runs through all of its iterations. Once the inner loop finishes completely, the outer loop proceeds to its second iteration. Then the inner loop runs completely again for that second outer iteration, and so on. The inner loop completes its full cycle for each single step of the outer loop.
Okay, that makes sense for iterating over, say, rows and columns. Finally, within a loop, are there ways to control its execution more finely? The source mentioned break and continue.
Yes, these are loop control statements. The break statement, when encountered inside a loop, either while or for, immediately terminates the innermost loop it is currently in. Execution jumps directly to the first line of code after that loop structure.
So it's a way to exit the loop early, like if you find the item you're searching for.
Exactly. If you're looping through a list searching for a specific value, once you find it, there's often no need to check the rest of the items. You can use if-item target.break to exit the loop immediately, which can be more efficient.
Okay. And continue, what does that do?
The continue statement is a bit different. When continue is encountered inside a loop, it immediately skips the rest of the code within the current iteration of the loop's body and jumps directly to the next iteration.
Skips the rest of the current iteration.
Yes. In a while loop, it jumps back up to evaluate the loop's condition again. In a for loop, it jumps to process the next item in the sequence. It doesn't exit the loop entirely like break. It just cuts the current iteration short and moves on to the next one.
When would you use continue?
It's often useful when you have a condition where you want to ignore the current item or skip processing for the specific iteration, but you still want the loop to keep going for subsequent items. For example, if you're processing a list of numbers and want to ignore any negative numbers, you might have, if number is 0 though, continue at the top of your loop body.
Ah, okay. So break gets you out of the loop completely, continue, it skips the current iteration and goes to the next.
Precisely. These control flow structures, if-else for decisions, and while for loops, along with break and continue, are absolutely essential. They are what allow your programs to be more than just a static list of instructions. They enable programs to react dynamically to different inputs or data and to automate repetitive tasks efficiently, which is really the core power of programming.
As you start writing programs that are more than just a few lines long, you'll quickly realize that having just one long, continuous list of statements becomes really hard to read, manage, and debug. You need ways to break down the complexity.
Exactly. And that's where functions come in. A function is essentially a named block of code that's designed to perform a specific, well-defined task.
You define it once, and then you can call it or execute it whenever you need that task performed.
Precisely. You define a function using the def keyword, followed by the name you want to give the function, then parentheses, and finally a colon done. The indented code block that follows is the function's body, the instructions that make up the task. Python?
Print. Hello there.
Okay. And you can define parameters inside those parentheses in the definition, like placeholders for data the function needs.
Yes. Parameters act like variables that are local to the function. They allow you to pass information into the function when you call it. Python.
Hashtag name is a parameter.print. Hello.
And the recommendation is to put a docstring right after the def line.
Yes, highly recommended. A docstring is a string literal, usually using triple quotes, placed immediately after the function definition line. It's used to document what the function does, what its parameters are, if any, what they mean, and what the function returns, if anything. Python. .def add numbers num1, num2. Calculates the sum of two numbers, args, num1. The first number, int or float, num2. The second number, int or float. Returns. The sum of num1 and num2, int or float, returns num1 plus num2. This documentation is incredibly valuable for anyone using or reading your code, and Python tools can automatically extract it. For instance, the built-in help function uses docstrings. Help add numbers would display that documentation.
Okay, so you define the function with def. How do you actually make the code inside it run?
You call the function. You do this simply by using the function's name followed by parentheses. Greet tooser. If the function definition included parameters, you need to provide corresponding values, called arguments, inside the parentheses when you call it. Greet tooser by name, Alice.
And what happens with the program's execution flow when a function is called?
When Python encounters a function call, the normal top-to-bottom execution pauses at that point. Control jumps to the first line of code inside the function's definition, the function body.
Okay.
The code inside the function body executes from top to bottom. When the function finishes, either by reaching the end of its body or hitting a return statement, control jumps back to the exact point in the code where the function was originally called. Execution then resumes with the very next instruction right after the function call.
Got it. It's like taking a detour to perform a specific task and then coming back to where you left off. Now, a really crucial concept with functions is variable scope, right? Local versus global.
Yes, absolutely crucial. Variables that you define inside a function's body have local scope. This means they only exist and are accessible within that specific function while it's executing.
So once the function finishes, those local variables just disappear.
Essentially, yes. Their memory is typically reclaimed, and you cannot access a function's local variable from outside that function. This is actually a good thing. It helps keep functions self-contained and prevents variables in one function from accidentally interfering with variables in another.
Okay, that's local scope. What about global scope?
Variables that are defined outside of any function, typically at the top level of your script file, have global scope. These global variables are accessible from anywhere in your script, both at the top level and from inside any functions defined in that script.
So a function can read the value of a global variable.
Yes, functions can read or access the values of global variables without any special keywords.
But what if a function tries to change or assign a new value to a global variable? There was a catch mentioned.
Right. This is where it gets slightly tricky. If you simply try to assign a value to a variable name inside a function, for example, my global variable equals 10, Python, by default, assumes you intend to create a new local variable with that name, scoped only to that function. This new local variable effectively hides or shadows the global variable with the same name for the duration of the function's execution. The assignment does not change the original global variable.
Oh, so assigning to a name that matches a global variable inside a function creates a local variable instead of modifying the global one, unless you do something special.
Exactly. If you genuinely need to modify a global variable from within a function, which, by the way, is often discouraged as it can make code harder to flood, you must explicitly tell Python your intention before you try to assign to it. You do this using the global keyword python.counter equals 0 a tag global variable.
Global counter, hashtag declare intent to modify the global counter. Counter plus 1, this now modifies the global variable. Increment counter, hashtag output will be 1.
Using global counter inside the function tells Python that any assignments to counter within this function should refer to the counter variable in the global scope, not create a new local one.
Okay, use global with caution. Now, functions can also send results back to the code that called them using the return statement.
Yes. The return statement serves two purposes. First, it immediately ends the execution of the current function, even if there's more code below it in the function body. Second, if you provide a value after the return keyword, return some value, that value is sent back as the result of the function call.
So the calling code can capture that result, like result, add numbers 5, 3.
Precisely. In that case, the add numbers function would execute, calculate 5 plus 3, hit return 8, and the value 8 would be sent back and assigned to the result variable in the calling code.
What if a function doesn't need to return a specific value? Or if it reaches the end without a return statement?
If you just use return by itself without a value, it still ends the function immediately, but it returns the special value. None. If a function's execution reaches the very end of its indented body without encountering any return statement at all, it also implicitly returns none.
Got it. And when calling functions, we can pass arguments either by position, matching the order of parameters, or by using keywords, parameter name value.
Yes. Positional arguments are matched based on their order. Keyword arguments let you specify which parameter you're providing the value for, which can make calls clearer, especially if there are many parameters, and allows you to pass them in any order. You can also define default values for parameters in the function definition, as a def power base exponent 2. If an argument isn't provided for a parameter that has a default value when the function is called, the default value is automatically used. This makes those arguments optional.
Functions really seem essential for writing code that's organized, reusable, and easier to understand by breaking tasks down. But what about organizing code on a larger scale, or using code written by others?
That's precisely the role of modules. In Python, a module is simply a file containing Python definitions and statements. It's a file with a .py extension that holds functions, class definitions, variables, basically any Python code. Modules allow you to logically group related code together and make it reusable across different programs.
And Python comes with a lot of built-in modules.
That's the standard library.
It does. Python's standard library is extensive and provides modules for a huge range of common tasks: file I/O, operating system interaction, networking, date and time manipulation, mathematical operations, math module, generating random numbers, random module, working with data formats like JSON or CSV, and much, much more. The source mentioned there are over 200 modules in the standard library. You don't need to install anything extra to use these. They come with Python.
And beyond the standard library, there's a vast ecosystem of third-party modules. Absolutely enormous. The Python Package Index, PyPI, often pronounced PyPI, is the main repository for third-party Python software. It hosts hundreds of thousands of packages, collections of modules, created by the community, providing libraries for virtually anything you can imagine, web development frameworks like Django or Flask, data science tools, NumPy, Pandas, SciPy, machine learning libraries, TensorFlow, PyTorch, image processing, game development, and countless other specialized domains. You typically install these using a package manager tool like pip.
Okay, so whether it's a built-in module or a third-party one you installed, how do you actually use the functions or variables defined inside that module in your own script?
You need to import it. There are a few ways to do this. The most common and generally recommended way is using the import statement followed by the module name. Import module name.
Import math, for example.
Exactly. Once you've done import math, the math module is loaded into your program's memory. To access anything defined inside the math module, like its squirt function for square roots, you need to use .notation .modulename.thing. So you'd write math.sqrt16.
Okay, import module name, then use module name.function name. What are the other ways to import?
An alternative is to import specific names directly from a module into your current script's namespace using the from.import statement. From module name import specific thing.
So from math import squirt.
Right. If you do that, the name squirt is brought directly into your script's scope. You can then call it just by using its name without the module prefix. You can import multiple specific names this way too. From math import squirt, pi.
That seems more convenient, less typing. Are there downsides?
It can be convenient, but the main downside is that it makes it less immediately obvious where the name squirt, in this case, came from. With math.sdmrt, it's crystal clear it belongs to the math module. With just squirt, you might have to look back at the import statements to remember its origin. It also increases the chance of name collisions.
Name collisions, what are those?
A name collision, or namespace collision, happens when you end up with two different things, like functions or variables, having the exact same name in the same scope, making it ambiguous which one you're referring to.
How can imports cause that?
Imagine you import squirt from the math module. Then later in your code, maybe you accidentally define your own function, also named squirt. Now, when you try to call squirt, which one gets called? The one from math or your own? It depends on the order, and it's confusing. Or, even worse, is the third import style, from module name imports read.
The asterisk means import everything.
Yes. From math, imports all the public names defined in the math module directly into your current script's scope, squirt, pi, sin, coses, etc. While this saves the most typing initially, it's generally discouraged in production code because it makes it very hard to know where names came from and dramatically increases the risk of name collisions. If two different modules you import using happen to define a function with the same name, the second import will silently overwrite the first one, leading to potential bugs that are hard to track down.
Okay, so import module name and using module names thing is the safest and clearest way, even if it's slightly more typing. And from module name import specific thing is okay if used carefully, but from module name import should generally be avoided.
That's the standard recommendation, yes. Clarity and avoiding ambiguity usually outweigh minor typing convenience in the long run.
Got it. Now, there's a very common pattern you see in Python scripts, especially ones that are intended to be both runnable programs and potentially importable modules. That if name equals main block, what exactly is that doing?
Ah, yes, the dunder name equals dunder main check. Dunder is short for double underscore. This is a clever mechanism Python uses to allow a script file to behave differently depending on whether it's being run directly or being imported into another script.
How does it know the difference?
Python automatically sets a special built-in variable called name, 2 underscores before and after, for every module. When you execute a Python script file directly from the command line, for example, python myscript.py, Python sets the name variable within that specific script to the special string value main. However, if that same myscript.py file is imported as a module into another script, example, inside another script.py you have import myscript, then Python sets the name variable within the imported myscript to the module's name, which is typically the file name without the .py extension, so it would be set to the string myscript.
Okay, so the value of name tells the script whether it's the main program being run or if it's just being imported.
Exactly. So the code indented under the if name equals main node line will only execute if the condition is true, meaning only when the script is being run directly. If the script is being imported by another module, name will not be main, the condition will be false, and the code inside that block will be skipped.
Why is this useful?
It's incredibly useful for separating the core reusable definitions, like functions and classes, in your script from the code that should only run when the script itself is the main program. For example, you might put function calls that actually start your program's execution, or maybe example usage or testing code for the functions defined in the script inside this block.
So if someone else imports your script just to use one of your functions, they don't accidentally trigger your main program logic or your test code.
Precisely. It prevents unwanted side effects when the script is used as a module while still allowing the script to be directly runnable. It's a fundamental pattern for writing reusable Python modules.
And finally, that help function we mentioned for function docstrings also works for modules.
Yes. If you're in the interactive Python shell, you can type help module name, help math, to see the documentation for the entire module, often including its main docstring and a list of functions classes. You can also do help module name.function name, example help math.sqrt, to get help specifically for that function, which usually displays its docstring. It's a great way to explore what modules offer and how to use their components.
Okay. Functions and modules seem absolutely vital for scaling up from simple scripts. They help manage complexity, promote code reuse, avoid repetition, and allow us to tap into the vast universe of code already written by the Python community.
Definitely. Once you start thinking in terms of functions and leveraging modules, your ability to build more sophisticated programs really takes off.
So far, we've mostly talked about handling single pieces of data, like numbers or strings and variables, or executing sequences of operations. But real-world programs almost always need to work with collections or groups of related data.
That's right. And Python provides some extremely powerful and flexible built-in data structures for this purpose. The two most fundamental ones you'll encounter constantly are lists and dictionaries.
Let's start with lists. What are the key characteristics of a Python list?
A list is an ordered, mutable sequence of items. Ordered. This means the items in a list have a specific position or index, and that order is preserved. The first item is at index 0, the second at index 1, and so on. Mutable. This means you can change the list after it's created. You can add new items, remove existing items, or change the value of items already in the list, all in place. Sequence of items. A list can hold multiple values called items or elements. These items can be of different data types within the same list. For example, a list containing numbers, strings, and even other lists.
How do you create a list?
You create a list literal using square brackets with the items inside separated by commas. For example, my list equals apple 3, true 3.14. An empty list is simply A.
And you access items using their index, starting from 0.
Yes. MyListVir would give you apple. MyList1 would give you the integer 3. Python also supports negative indexing, which counts from the end. MyList1 gives you the last item, 3.14 in this case. MyList2 gives the second to last item, true, and so on.
Immutable means I can change it, like MyList1 E5.
Exactly. After that assignment, my list would become apple 5, true, 3.14. The original integer 3 at index 1 has been replaced. This ability to modify lists in place is a key difference from strings, which are immutable. You can't change a character within a string directly.
Okay. The sources mention a lot of common operations and methods for lists. How do you find out how many items are in a list?
You use the built-in len function, just like with strings. Numetum will len my list.
How do you add items to a list?
There are a couple of main ways. The append method adds a single item to the very end of the list. mylist.append. New item. The insert method allows you to insert an item at a specific index. mylist.insert1, another item, would insert another item at index 1, shifting subsequent items down.
And removing items.
Several options here too. mylist.remove value. This removes the first occurrence of the specified value from the list. If the value isn't found, it raises a value error. mylist.popIndex. This removes the item at the specified index and returns it. If you call pop without an index, mylist.pop, it removes and returns the last item from the list. This is quite common, the del statement. You can use del with an index to remove an item, del mylist 0. You can also use del with a slice to remove multiple items, del mylist 1.3.
Okay, lots of ways to modify them. What about working with lists of numbers, finding min, max, sum?
If your list contains only numbers or types that can be compared summed, you can use the built-in functions min_mylist, max_mylist, and sum_mylist directly.
Now, there was a really important warning in the source about copying lists. Just using rel doesn't make a real copy.
Ah, yes. This is a crucial concept related to mutability and how Python handles variables referencing objects. If you have a list old list 1, 2, 3, and you then write new list old list, you are not creating a new independent list.
What are you doing then?
You are simply creating a new name, new list, that points to the exact same list object in the computer's memory that the name old list already points to. You have two names referring to one list.
So if I then change something using newList, like newList.append4,
you are actually modifying that single original list object in memory. Since old list still points to that same object, If you then check the value of old list, you'll see it also now contains the 4. They are not separate copies. They are aliases for the same mutable object.
That could lead to very confusing bugs if you're not aware of it. How do you create a truly independent copy then?
There are a couple of common ways to create a shallow copy, which is usually sufficient for lists containing simple, immutable items like numbers or strings. Use the copy method, newlist.newlist.copy. Use slicing.newlist, old list. This slice creates a new list containing all the elements from the old list. Use slicing. Both of these methods create a brand new list object in memory with its own copy of the elements from the original list. Now, modifying new lists will not affect old lists and vice versa.
Okay, use .copy, or for making independent copies. What about sorting lists?
2 main ways again. The sort method modifies the list in place, mylist.sort. By default, it sorts in ascending order. You can sort in descending order using mylist.sort. Reverse true. Since it sorts in place, it doesn't return anything. It returns none. The built-in sorted function takes any iterable, like a list, as input and returns a new sorted list, leaving the original list unchanged. New sorted list sorted, mylist. This is often preferred if you need to keep the original list intact.
And reversing a list.
Similar pattern. Mylist.reverse reverses the list in place. The reverse function returns a reverse iterator, which you can convert to a list if needed, like list reversed mylist, leaving the original list unchanged.
And iterating through lists is typically done with a for loop for item in mylist.
Yes, that's the standard, most Pythonic way to process each element in a list one by one.
The source also mentioned list comprehensions as a more concise way to create lists.
Yes, list comprehensions are a very powerful and expressive feature of Python. They provide a compact syntax for creating a new list based on an existing sequence, or other iterable, often involving transforming or filtering elements. The basic syntax is expression for item in sequence if condition.
Can you break that down?
Sure. For item in sequence, this is the loop part, iterating over the source sequence if condition, optional. This is a filter. Only items from the sequence for which the condition is true will be processed, expression. This is applied to each item that passes the filter, or all items if there's no filter, and the result of this expression becomes an element in the new list being created.
So squares x for x in range 10 would create a list of the first 10 square numbers.
Exactly. It iterates through numbers 0 to 9, range 10. For each number x, it calculates xx, and that result becomes an element in the new squares list.
And positive enums, equals n for n in my numbers, if n0 would create a new list containing only the positive numbers from my numbers.
Precisely. It iterates through my numbers. The if n0 acts as a filter. Only if n is greater than 0 is the expression, which is just n itself in this case, included in the positive enums list. List comprehensions can be much more readable than equivalent code using append inside a traditional for loop once you get used to the syntax.
Okay, lists are ordered, mutable sequences accessed by index. What about dictionaries? How are they different?
Dictionaries, dict, are another fundamental collection type, but they work differently. A dictionary is essentially an unordered, in older Python versions, though insertion order is remembered in modern Python, collection of key-value pairs.
Key-value pairs?
Yes. Each item in a dictionary consists of a unique key and its associated value. Think of it like a real-world dictionary where you look up a word, the key, to find its definition, the value.
How do you create a dictionary?
You use curly braces. Inside the braces, you specify key-value pairs separated by a colon I with commas between the pairs. Madic key 1, value 1, key 2, value 2. For example, student name, Bob, age, 22. Major, physics. An empty dictionary is just a, or you can use dict.
So instead of accessing items by numerical index like lists, you access values using their keys.
Exactly. You use the key inside square brackets. Madic t. Using our example, student name would give you the value Bob. Student age would give you 22.
What are the rules for keys?
Keys within a dictionary must be unique. You can't have 2 items with the same key. Also, keys must be of an immutable type. This means you can use strings, numbers, integers, or floats, or tuples if they contain only immutable elements as keys. You generally cannot use mutable types like lists or other dictionaries as keys. Values, however, can be of any type: numbers, strings, booleans, lists, even other dictionaries.
Okay, keys are unique and immutable. Now, you said accessing with madic key works, but what if the key
Yes, if you try to access a key using square brackets and that key is not present in the dictionary, Python will raise a key error. This is a common exception when working with dictionaries.
So how do you safely access a value if you're not sure whether the key exists to avoid that key error?
The safer and often preferred way is to use the dictionary's get method, .mydict.getKey.
How does get work?
mydict.getKey will look for the key. If the key exists, it returns the corresponding value, just like the square bracket access. However, if the key does not exist, get does not raise a key error. Instead, it returns the special value, none by default.
Returns none instead of crashing. That's useful.
Very. And get can also take an optional second argument, which is a default value to return if the key is not found instead of none. For example, count wordcounts.get the 0 would return the count for the word the if it exists, or it would return 0 if the is not found as a key in the word counts dictionary.
That's really handy. Okay, how do you add new key value pairs to a dictionary or change the value associated with an existing key?
You use assignment with the key in square brackets. mydict_key, Aloria.
And that works for both adding and modifying.
Yes. If the key already exists in the dictionary, this operation updates its associated value to the new value. If the key does not already exist, this operation adds the new key value pair to the dictionary. It's quite convenient. So student age 23 would update the age, and student age 9001 would add a new key value pair.
How about deleting items from a dictionary?
You typically use the del statement with the key, del mydict_key. This removes the key value pair associated with that key. Just like square bracket access, if you try to del a key that doesn't exist, it will raise a key error.
Okay. Can you iterate over dictionaries like you can with lists?
Yes, you can. If you use a simple for loop directly on the dictionary, like for item in mydict, it will iterate over the dictionary's keys by default.
Just the keys?
Yes. So for k in student.print, it would print name, age, major, possibly in a different order in very old Python versions, but usually insertion order now. If you want to iterate over the values, or over both the keys and values together, you need to use dictionary view methods.
View methods?
Dictionaries have methods that return special view objects, which are iterable.mydict.keys. Returns a view object containing all the keys, mydict.values. Returns a view object containing all the values, .mydict.items. Returns a view object containing key value pairs as tuples, key value.
So if I want to loop through both keys and values, I'd use .items.
Exactly. The most common pattern is for key, value, and mydict.items. Hashtag now you have access to both key and value in the loop body. This lets you easily work with both parts of each pair.
Like lists containing lists. Can dictionaries contain other dictionaries? Nested dictionaries?
Absolutely. Dictionary values can be any type, including other dictionaries. This is extremely useful for representing structured or hierarchical data. Think of JSON data, which often uses nested objects that structure maps very naturally to nested Python dictionaries.
And accessing values in nested dictionaries would just involve chaining the key lookups, like data user address city.
Precisely. Each key lookup returns the corresponding value, which might be another dictionary, allowing you to drill down through the structure using successive square bracket lookups.
Wow. Lists and dictionaries seem incredibly versatile. They really are the workhorses for storing and organizing collections of data in Python.
They truly are. You'll find yourself using them constantly for all sorts of tasks, from storing simple sequences of inputs to managing complex configurations or representing structured data from files or APIs. Understanding how they work, their differences, ordered index list versus unordered keyed dictionary, their common operations, and especially that mutability copying behavior for lists is absolutely fundamental to effective Python programming.
We have certainly covered a lot of ground today, focusing on these core building blocks. We went from the very first step of getting Python installed and understanding those often scary error messages.
Turning errors into diagnostics, yeah.
To handling different data types, making decisions with if loops, repeating actions with while and for loops, organizing code into reusable functions, and leveraging modules.
And finally, using lists and dictionaries to manage collections of data effectively. These really are the foundations you'll use in almost every single Python program you write, no matter how simple or complex.
These are the concepts that, as a learner, you really need to practice and get comfortable with. Experiment with them.
Absolutely. And while we focus on these fundamentals today, it's worth briefly mentioning that Python offers many more advanced concepts that build upon these foundations, allowing you to tackle more complex problems and structure larger applications in sophisticated ways. We can't dive deep now, but knowing they exist might guide your future learning.
Like object-oriented programming, or OOP.
Right. OOP is a major programming paradigm that helps manage complexity by grouping related data, called attributes or fields, and the functions that operate on that data, called methods, together into units called objects. You define blueprints for objects using classes. Concepts like encapsulation, inheritance, and polymorphism are central to OOP and are very powerful for building large, maintainable systems.
And recursion was mentioned.
Recursion is a fascinating programming technique where a function solves a problem by calling itself, but with a slightly simpler version of the problem each time. It needs a base case condition to stop the self-calls. It can be a very elegant way to solve certain types of problems, like calculating factorials, processing tree-like data structures, or solving puzzles like the Towers of Hanoi mentioned in the source.
File handling, too, interacting with files on the computer.
Essential for many real-world applications, Python has built-in functions like open to read data from files, like text files, CSVs, JSON, or write results back out to files, allowing your programs to persist data or interact with external data sources.
And you briefly touched on Python's role in data science.
Yes, Python has become incredibly dominant in data science and machine learning. This is largely thanks to a rich ecosystem of powerful third-party libraries built on the foundations we discussed. Libraries like NumPy, for efficient numerical computations, especially with large arrays and matrices, pandas, for data manipulation and analysis. It introduces structures like the data frame, which is like a superpowered spreadsheet or table in your code, making it easy to clean, filter, transform, and analyze structured data. Matplotlib, and others like Seaborn, for creating a wide variety of data visualizations, plots, graphs, charts to understand data and communicate findings. Matplotlib, and others like Seaborn. These libraries, combined with Python's general-purpose nature, make it a go-to language for the entire data science lifecycle, from acquiring and cleaning data to building predictive models and reporting results.
So OOP, recursion, file handling, data science libraries, these are all exciting areas to explore once you feel you've got a solid grip on the fundamentals we covered today.
Exactly. They show how Python scales from simple scripts to complex applications and specialized domains. But they all build on the core concepts of variables, types, control flow, functions, and basic data structures.
Okay, so let's just quickly recap this foundational deep dive, this tutorial journey. We started right at the beginning, making sure you have the Python interpreter actually installed on your machine, navigating the various options for Windows, macOS, and Linux, and understanding why things like the command line and the path variable matter.
The essential setup. Then we demystified errors. We clearly distinguish between syntax errors, the grammatical mistakes caught before your code even runs, and exceptions to errors that pop up during execution when something goes wrong operationally. We emphasize reading the traceback message to understand the type and location of the problem, turning that red text from a stopper into a helpful guide.
And crucially, we showed you how to build resilience using try.except blocks, how to anticipate specific errors, like value error from bad input or file not founder, and provide alternative actions, preventing your program from just crashing. We also touched on raise for signaling your own error conditions, and finally for guaranteeing essential cleanup actions like closing files.
From there, we dove into the absolute nuts and bolts of writing code, getting input from the user with input, and remembering it always returns a string, displaying output and formatting it using the print functions arguments like sep and end, and the cornerstone concept of using variables with the assignment operator to store and manage data, including naming rules and the PP8 snake case convention.
We explored Python's fundamental data types, integers int, floats, float, strings, newsr, and booleans, true-false. We covered how to convert between them using functions like instar, etc. Look at how Python handles arithmetic operations, including traverse floor division with AND-E, and the modulo operator %, and importantly, discuss the nature of floating point numbers and why direct equality comparison can be tricky.
Then we moved on to controlling the flow of execution, making decisions based on conditions using if, elif, and else statements combined with comparison and logical and or not operators, and automating repetitive tasks using loops. The while loop, repeating as long as a condition is true, watch out for infinite loops, and the for loop, iterating over sequences like strings, lists, or numbers from range. We also covered using break to exit a loop early and continue to skip to the next iteration.
We then focused on organizing code, creating reusable blocks of logic with functions, def, understanding parameters, inputs, and return values, outputs, the critical concept of variable scope, local variables inside functions versus global variables outside, and the importance of documenting functions with docstrings. We also introduced modules as files containing Python code, how to import them to reuse code, standard library or third party, and that essential if name main pattern for making scripts both runnable and importable.
And finally, we explored the two primary built-in data structures for handling collections. The ordered, mutable index list, covering its operations like append, insert, remove, pop, sort, and the crucial difference between assignment and making true copies, .copy, and the key value paired dictionary, accessed by unique immutable keys, covering adding updating items, deleting del, safe access with .get, and iterating over keys, values, or items.
So this whole deep dive was structured to give you that foundational map, pulling directly from reliable sources like the official docs and established learning materials. The goal was to equip you with the core vocabulary, a solid understanding of how these pieces work together, and the confidence to actually start writing and debugging your own Python codes, like we've handed you the essential toolkit.
Absolutely. And the single most important thing you can do now is practice. Seriously. Open your terminal or code editor, write a tiny script, make it print something, ask for input, do a calculation, make a simple if statement, try a for loop with range, intentionally introduce syntax errors or logical errors and see what the traceback looks like, practice reading them. Use try.except to handle an expected error, like trying to convert non-numeric input to an integer. Experiment with adding items to a list or looking things up in a dictionary.
It's that hands-on experience that really cements these concepts.
It really is. The more you write code, even tiny little programs, the more these ideas will click and shift from abstract concepts to practical tools you know how to use.
So let's end with a thought for you to take away. Consider this. Now that you have a grasp of these absolute basics, how Python runs code, how to store different kinds of data, how to make choices and repeat actions, how to handle basic errors, and how to use simple collections like lists, what's one tiny, maybe even trivial problem or task in your own daily life that you could potentially write a very simple program to help with.
Doesn't have to be world-changing.
No. Maybe it's converting Celsius to Fahrenheit, calculating the tip on a bill, counting how many times a specific word appears in a sentence you type in. Just think of one small, concrete task. Then, try to sketch out how you would use only the tools we've discussed today: input, print, variables, maybe an if statement or simple for loop, perhaps storing something in a list to build a program that does that one thing.
Starting small and achieving a smart success is incredibly motivating.
Exactly. It shows you the power you already have with just these fundamental building blocks. The journey of writing useful, interesting, complex programs literally begins with putting these simple pieces together. Go try it.